So good morning, all of you. It's nice to have you again in today's class. We were discussing two problems yesterday in the class. In fact, we are trying to attempt these two problems, and I asked you at least go through this problem statement and try to understand how it can be done. Can I see the hands, those who have done it and they found they have successfully completed this? Please raise your hands if you have done it, or if you have attempted also, that is also fine. Good. So I see Prashasti, Anuj, Yatin, Naeem. So 4 hands. It's fine. So at least you have attempted. That's really nice. So let us try to understand this problem, how we can do that. So the problem statement I have already read yesterday. You have an actuator over here, which is a cylinder. And whenever you make the pressurized fluid entering into the cylinder from either side, you will be able to control the motion of the cylinder forward and backward. Now that is being controlled by a direction control valve, which we discussed briefly in one of the class. So this is your direction control valve over here. And this direction control valve is a two position valve and which can be actuated by the two solenoids over here, one Y1 and one Y2. So you can energize one of the solenoid to make it moving forward or backward. So if you energize one Y1, it will go forward. And if you energize solenoid 1Y2, it will go backward. That is how you will be controlling the direction of the flow of the fluid, and then your cylinder will be controlled. Now the problem statement says that you have a hot pressing die. So this is a hot pressing die over here, which is connected with the cylinder here. And the name of the cylinder is 1A. And then you will be sealing material. So packaging material is to be sealed. So there is something on the roll and which is to be sealed by this. By applying a heat and pressure. So then with the help of this cylinder and this hot pressing die, you will be applying heat and pressure here. Now by pressing a start push button, so functionality what we want is that by pressing a start push button, the cylinder should advance. That is what we want, that the heating rail is in advanced position and the packaging material is heated. So once it is fully extended, then the cylinder will be applying pressure through this hot pressing die and the packaging will happen and along the adhesive strip, and after this heating, the 5 seconds after this you have to retract. So operation will take 5 seconds and then heating rail will return to its start position. So this is the problem statement. So as I was mentioning, you have to attempt by making a PLC connection diagram and then you have to build a ladder logic. So these are the kind of problems you should be familiar with. These are very basic logic program that you can easily build, and once you understand this, certainly then you can build a complex programs as well. So let us try to attempt this problem. So as we always start, that how many DIs and DOs, that is what I keep on asking you, and that is how every problem has to start with it. So how many digital inputs, digital outputs we require to control this functionality? So we have two sensors over here, one 1B1 and 1B2, that to sense the two end position of the actuator. And then we'll have one S1 as a start push button. So we'll be requiring three digital inputs over here. So three DIs will be there, and to control the two solenoids, we'll require two DOs actually. So that is how we have identified that, and now it's time to draw the connection diagram. So it's a simple one. I'm not going to draw complete again because we have already done that. What you can do that you have, so you can just draw the PLC block here, and then you'll draw the IO modules like this. This is just a representation of that so that you'll understand that. And then you will be connecting the inputs on this side. So I'm just drawing the representation of the screw terminal on the PLC. And same way you will be having these screw terminals on the output side. So in this case, we will be connecting all three digital inputs here. So this digital input, this digital input, this digital input. So here I have just connected consecutively over here. So if you can see here, so I can have 1B1 connected here. I can have 1B2 connected here. I can have S1. So I'm not drawing the connection, but I'm just marking them. When you will draw, you have to draw the complete circuit, how the proximity switch will be connected and how the start push button will be connected. On other side, output side, I will have 1 by 1 and I will have 1 by 2. So that's how the connection diagram can be drawn. And this is your PLC. I hope this is understood by everyone. So basic connection diagram you can easily build. So once you identify the IOs, you can easily build the connection diagram for the PLC. Now, next part left out is that how to draw the ladder logic. So then we will be attempting the ladder logic part. So what you can do, we can have again 2 vertical lines being drawn over here. And now we will attempt step by step. So good thing is that if you can identify the step itself, so what is the first step here? What will happen? First step is basically that when you press, if you read the problem statement, you can see that when the start push button is pressed, heating rail is advanced. So this is the statement here. When you press a start push button, the heating rail is advanced actually. So in that case, what we want, so step 1 is that S1 is pressed and then you would like to extend. So S1 is pressed, you would like to extend 1 by 1. That is how it can be done. Fine. And then we'll go to the next step. So let's first draw the logic for the first step. Who will tell me the logic for the first step? What should I draw? Anyone, you can raise your hand and then I can ask. Anyone who can tell me what should be the first rung that I should draw?
Sir, first rung should the examine S1 if
Correct.
it is closed or not, and also the sensor one, the piston
Correct.
is in back position or not.
So we'll use 2 XIC instructions here. One is for the S1 and one is for 1B1. It's right, Anuj. And then what we will be doing, drawing on other side?
Energize the solenoid.
So then we'll just place the
One energize.
Okay, so you have to tell me the instruction because see, PLC didn't understand whether it is a push button, whether it's a proximity switch, whether it's a solenoid. The PLC will only understand the instruction and the address. So we need to just keep that in mind. So whenever we say what I have to draw here, you have to just mention I have to draw the XIC instruction and then I have to draw the OTE instruction. So this is the OTE instruction, and which is basically, see, we are writing this S1, 1B1, 1 by 1 labels for our understanding. PLC will not use anything out of this while execution, whether it's an S1 or S2 or 1B1. That is only for our understanding. Good. So once I draw this rung, the second thing I have to do is I have to write the addresses of the these XIC and OTE instructions. So who will tell me the address? What should be the address for S1?
I semicolon 0.0/0.
I
Semicolon.
So I semicolon is not there at all. It's a colon only. I1 colon
0.0/0.
correct.
0.
0.0/0. Good.
Yeah.
So this is the address for the S1. Similarly, I will put the address for S1B1 I1 colon 0.0/1. No, I think something is wrong. S1 is not connected to the 0 actually, so it has to be different. You have to look at the connection diagram that we have drawn.
Okay, sir. So 0.0/2.
2, yeah, this is at the 2, and then your 1B1 is at 0 actually.
Yes, sir.
So this is understand. And what should be the output address? So O0 colon 0.0/0, all zeros. Good. Is this clear to everyone?
Yes, sir.
Yes. Okay, good. So this is a small class, so I will look forward that all of you can participate. That will be nice. You will also be understanding, and I will also get an information whether you have understood it or not. Because this is more important if you understand in the class rather than just looking after the slides later on and then spending additional time. I'm sure that whatever you understand in the class, that will be good enough to understand the course. If you are sincere here, attending the problem the way I will be advising, then that this will be good enough to at least learn in the course. So once we have done this, your first requirement has been done actually. So this problem statement, first requirement is done. So this is okay now. Now the operation will take 5 seconds and then heating rail will return to its start position. This is the important part now we have to attempt. So this is the step 2 over here. So step 2 now we need to draw as another rung over here. So what should be the first instruction that I should draw? If you tell yourself, otherwise I will ask in the class. Yatin, can you tell me? What should be the instruction?
Sir, I use an XIC instruction for 1B2, sir.
Okay, good. So we will place one XIC instruction and this will be for 1B2. And then what should I connect to this instruction further?
Sir, in the output, I have turned on the timer T on.
Okay, good. So good. So we'll place basically the timer block over here. That is what is required in the program. What we want actually, once the cylinder is fully extend, it means it reaches to the forward end position. The input that I will be getting is 1B2. So that I will be using to start the timer, because I would like to start the time immediately the rail touches the job. This heating die will touching the job. So then only I will be starting the timer to start counting 5 seconds after that. So that's how we will be keeping this as a T on here. So just start that counting of the time and then make sure that 5 second lapsed actually. So what will be the parameter that I will be setting inside this on delay timer? Who will tell me? Let me ask someone actually. Kumar Vishes.
Yes, sir. Sir, preset value should be 5 seconds.
First, let's start from the first instruction. That is the address. You tell me the address that is to be given for T on.
Sir, T4 colon 1.
0. We can start from 0. Why to waste a first timer itself?
Yes, sir. 0.
T4 colon 0. Next will be the time base.
Yes, sir. Time base we can give 1 second.
1 second, fine. And then we'll go for the preset value 5. That is good. And accumulated value will be 0 in the beginning. So these are the 4 parameters you can put into the on timer block. And then this is your enable and this is your done bit actually, like this. Yeah, that is fine. So this is good, and we'll put the address for the 1B2 instruction. So that will be the address, that is I1 colon. Who will tell me this address? 0 colon 0 slash. What should be the value?
1, sir.
1.
1. Good. So we'll have 1. So nice. I think you all learned this very well actually. So that's how we are able to make the ladder logic for this problem. So we reached up to this state that once the cylinder is fully extended, your timer will start and your count in the accumulator will start incrementing. So this count will keep incrementing 1, 2, 3, 4, 5. And what will happen after 5 seconds? What will happen after 5 seconds?
This is retract.
Done bit enabled.
Yeah, so your done bit is 1 actually. Done bit is set to 1. So the value of the done bit will change. Till 5 second done bit state is 0. And after the 5 second lapse, done bit will be 1 actually. Now our requirement is that after the 5 seconds, I would like to retract the cylinder actually. So it means that I have to energize the solenoid 1y2 to make the cylinder go back, or the retraction part. So what I have to do, then I will be utilizing the done bit status or the state here to control my 1y2. So this is the done bit. Now how shall I write the address for this done bit?
So T4 colon 0 slash DN.
Good. So I think this is the way. So it's well learned actually. That's really nice. So this is the way we finish the program. That's all. 3 statements, 3 lines. We did the program. This is rung 0, this is rung 1, and this is rung 2. And you are all done. So the functionality of the basic requirement for this kind of a small job can be easily done with these 3 rung of the instructions, and we are all set. Once you transfer this program into the PLC, and if you connect them physically the way I have just mentioned in the connection diagram, your circuit will be functioning. So that's good actually. So this is done. Yes.
Sir, shouldn't we connect a reset instruction for resetting a timer?
Reset is
end.
not required. So see, reset will happen automatically the moment cylinder will retract. The good thing is that na, say in the T on and T off, you need not to worry about the reset instruction at all. So because what will happen if you see here, the moment you energize one Y2, this second solenoid get energized, your cylinder will retract. This will go back, and the moment it will go back, 1B2 will be 0. Fine, because you are sensing the forward position of the cylinder with the 1B2, and the moment 1B2 is 0, once this input is 0 to the timer, timer got reset. That is how we have seen the timing diagram yesterday, that the moment input falls 0, this input that is there, if it falls 0, everything reset actually.
Okay.
Okay. So just refer to that timing diagram that we discussed. So we have understood that this timer will keep running till this input is on. The moment this input goes false, the timer will reset. So that is how you need not to reset. The moment 5-second lapse and you retracted the cylinder, the timer will reset and ready for the next cycle. Okay. Done. So next example is little interesting one. So let's attempt this one also. Anybody is able to successfully attempt this? Just raise your hand. So Yatin has already done. Good. Anuj has already done. Good. What happened, Anuj? You raise your hand and you brought it down. Yeah. So Aman has done. Nice. So good, let's try to understand how we will build the logic. So what I will be just explaining are the simple way to understand how to build the logic. Whenever you come across in a complex statement, multiple things to be done in a requirement like this or this or even a more complex requirements, you have to first break down the whole problem into simpler steps actually, and you try to visualize what will happen actually. So as a first step, what should happen? As a second step, what should happen? And then we will be building the ladder logic for those steps accordingly. So let's try to do this now. Read the problem statement again. If you have a S1 as a push button, once you actuate that, cylinder is to advance and eject a workpiece and then retract again. It means that from S1, my first requirement is that my cylinder will be extending and then it will be retracting on its own. And we'll follow the same cylinder diagram which we have seen in the previous statement, a previous problem, that you will be having two sensors, 1B1, 1B2, and we will be having two push button S1 and S2 for this problem, and then you will be operating it. So I think the configuration will remain same. I will just write down that your 1B1, 1B2, S1 and S2. These are the digital inputs basically in your system, and we'll connect this to 0, 1, 2, 3 ports. So this is how the input is being connected. Similarly, you can have, let's draw it. There's nothing. Yeah, so you will be having an output. So you will be having one Y1 connected over here and one Y2 connected over here. So there are two outputs that you require. So with this understanding of the IOs, let's start drawing the ladder logic. I'm sure you will be able to think about the logic part. That is more important because instructions are just an understanding how to write the logic, but basic logic thinking should happen by you only. So we'll start with the step one. Step one says that whenever you press S1, what we want. So S1 is pressed, 1B1 is true because we want to check the cylinder is at the retracted position, and then only we would like to execute the cycle. And then after this, 1Y1 should be energized because we would like to extend the cylinder. This is the first step. What would be the second step? Once the cylinder is fully extended, fine. So which will be the input that you will be getting? Let me ask Sachin.
Sir, was this question given in last class? Sir, I couldn't read it in this time.
Okay, so now today, are you reading this? I have already mentioned here. So if you have a S1 push button here, The cylinder is to advance actually. What we want, the way we have done in this previous problem, whenever you press S1, your cylinder should move forward actually. This is the first thing that we are trying to attempt over here. So we are sensing the 1B1, that is the retracted position of the cylinder, one, and then you will be pressing S1. And these two combinations will energize the solenoid to extend the cylinder. That is the first statement that we would like to do. And that is what we have written. That when your S1 is true, once your 1B1 is also true, we would like to extend the cylinder with the 1Y1. Now my question is that when the cylinder is fully extended, I would like to retract the cylinder. And we have done the similar problem of the automatic retraction. So what would be that input that we will utilize here?
Sir, we can.
How you will come to know that cylinder is fully extended?
Sir, when the sensor, the other sensor, which is used.
The name of this sensor actually?
So 1B2.
Correct. So we will now sense the extended position of the cylinder with 1B2. And what will I do after I get this 1B2?
Sir, we will retract.
So what exactly will be the output instruction of what exactly I will be energizing?
So 1Y2.
Yes. So 1B2. And then I would like to energize 1Y2. So the cylinder will retract. So now this is your first step. When S1 is true and 1B1 is true, so we'll put AND here. Your solenoid 1Y1 will energize. Second instructions, once the cylinder reaches to the forward position, the 1B2 will get energized. It will give a signal and which will control the retraction part of the cylinder with the help of a solenoid 1Y2. So this way your cylinder forward motion is done, and this way your cylinder retracted motion is done. So the first requirement of your problem is met. So if you look at this statement here, once the push button S1 is actuated, cylinder is advanced, eject a workpiece, and then retract again. So this requirement is done by these first two steps. So let us draw the logic for this. I think that is very clear. Once you have clarity on this kind of thing, then you can easily draw, because we need to sense the two inputs over here. So Sachin, which instruction we will use here?
Sir, XIC for both S1 and 1B1.
Correct. Two XIC instructions in series that we will be using here. Yeah, Kumar, you have raised your hand.
So we don't have any output for ejection of the workpiece here?
No, so cylinder will be pushing the workpiece. So that's all we want actually. So in this case, if I just roughly draw, your gravity fed magazines are normally like this. So you have a stack of the objects like this. So in fact, I am not having a figure right now like this. So these are the parts that are being stacked vertically in the magazine. And then there's a part here which is on the table, and your actuator is here actually. Now actuator is basically pushing this block which is at the bottom. So it will come out. So as you are energizing the actuator, this block will come out and the second block will fall down. So that is what the gravity fed magazine configuration is. So that is what I want. Once the cylinder get pushing the block is forcefully exit basically out of this magazine. It will be coming out of the magazine. So I will be sensing only this position of the actuator, that the block is extended. That's once the cylinder reaches to this position, it means that the cylinder has already pushed the block out of the magazine. Is this clear?
Yes, sir.
Okay. So let us go now to complete the logic here. So we have this S1, we have this 1B1 here. And for the first, we would like to energize the 1Y1. That is what the first instruction we have done here. The second instruction is clear, that you will be again reading 1B2 over here. That is 1B2 here. And then you will be energizing the second solenoid 1Y2. So your first two steps are being done. Now, interesting part comes now. What we want to achieve after this. So first of all, you have to count the parts, because there's an event associated with the counting of the parts. So 15 parts are to be ejected in this way. So 15 times if you press the S1 push button, your 15 blocks will be coming out of this magazine. and when 15 parts being ejected. So that will come to the next statement later on. First, let's count these number of parts. So how you will count those number of parts? So I will be utilizing the same input that is coming from 1B2. What we can do, we can use the same input because that is indication that the block is coming out of the magazine. So what I will do, I will add a counter instruction over here. Let's add a counter block over here. So we'll use. So CTU block will be used, and I will be using the same input which is coming from this 1B1. You can put in a parallel block here, which is in a counter block in this case. And in this case, once you have this instruction, what are the parameters that I will be writing inside it? Anyone? What should be the address here?
C5 colon 0.
C5 on
C5 colon 0. Right. So C5 is the counter file. 5 is the file number, and then we will be using first counter. So we'll be using colon 0. So that is what the address of this. And we will be writing the preset value here because there's no time base. So preset value will be 15 and your accumulated value will be this. So this is your pre value and this is your accumulated value. This is the time, the counter address. So once you set these parameters, then this is done. The count up CU is there. Fine. So this counter is now taking care of how many blocks are being ejected. Fine. And then you will be having a done bit also here. Like this. So this way, now I will be keeping record of the objects being counted, but what I will do after the 15 objects being ejected, that is the logic. That's only logic that is important for this problem. So once we understood that once the 15 blocks are being ejected, the done bit will be set. That is the important part to understand, that your done bit will be set here. And then what will happen? So once this done bit is set, what should I do now? Naeem Akhtar.
Sir, we need to reset the setup.
No, setup means what? I need the instruction basically. What should I do? So first of all, I will be reading the done bit of this counter. That is fine. But what should I do after that?
So along with the done bit, we need to connect another switch S2 in series with the done bit.
Okay. So if I just take this instruction, let's see that we will be using this C5 colon 0 slash done bit. Connect another input here, which you are saying, and this will be the S2. And
Yes,
what
sir.
should I do here?
So, sir, the counter reset.
So I will be resetting the counter. Fine. So what will happen once your done bit is set, but you are dependent on the S2 to reset the counter. So if you read the problem statement here, what we want here, let's try to read the problem. This is very important to understand what is expected in the problem and what exactly I will be attempting in the logic itself. So the problem says that, for example, there is an operator who is operating this. So he is operating the whole system by the push button S1. Whatever I have added over here, will that be preventing the ejection of the 16th part? See, the problem here is that 15 parts being ejected, it should no longer be possible to trigger a cylinder movement. What we want, see, operator is not knowing this. Operator is again pressing the push button S1 again to eject the 16th part. Now, is my logic preventing that? So I don't see that anything is preventing if I press S1 again. So the same circuit what you have already drawn, see the bottom one will come into action if you press S2, but I'm not interested in pressing S2 right now. Because operator has nothing to do with S2. Operator is only responsible for operating the system by push button S1. So if I press S1, first of all, if I press S1, will it stop the ejection of 16th block?
No, sir. Sir, I think we will have to unlatch the one by one.
No,
Yeah,
sir.
but there is no latching right now. So we'll go one by one. Let's talk about the problem statement one by one. So first of all, this logic is not going to interfere in the operation by the S1. Is that
So
clear?
we saw one another instruction greater than or equal to yesterday.
No,
That
no,
can be used.
but I have not taught you that instruction. Let's not worry about that. That we'll discuss comparison instruction today. Let's try to do without that instruction. Let's not worry about the comparison instruction right now, because here we are already having a preset value. We already getting an indication that 15 parts are being ejected, and your done bit is basically a good indicator of that. Now I have to utilize the done bit somewhere. For what? For what I have to utilize the done bit? I have to stop the ejection of the 16th part. That is the most important part. Now try to understand how can I stop the movement of the cylinder. Then I can quickly narrow down that I have to do something here.
Sir,
Because
we can use normally open S2 in series with S1.
correct. So let's evaluate all the options. See, that's a good part, that we need to evaluate, think with all the options, and then simulate whether my circuit is going to meet the functional requirement or not. So first of all, this one that Naeem has suggested, we all agree that this is not going to help in stopping the 16th part. So let's go for the next change. Aman, you are saying something. Let's see that. We'll try that, your option. So what is your suggestion? How we will do that?
Open in series, XIO in series with S1 and 1B1.
No, first you explain what should be the logic, what we should be looking forward, so that everybody will understand why we'll be adding that instruction, or there's another instruction. First, we need to think about what exactly we want to do. So once we are sure that 15 parts ejected, we have seen that the done bit is set now. Now what I have to do, I have to stop the operator to eject the another part. The rung or the logic that is responsible for movement of the cylinder for ejection of the part from the magazine is the first rung, or this rung 0 basically here. So rung 0 is responsible for that. Now I have to do something. It means what I have to do, whenever done bit is set. So you write your statements like this only. First you write the descriptive statement, what you want to achieve. Once you are clear about that statement, then we will talk about the logic. So once I understand that, once the done bit is set, I have to stop this 1y1 from energizing. So even the operator is pressing S1, this is also true. Both are true. This is true. This is true. But still I want to stop this. I want this to be false. So this is the requirement when the done bit is set. When done bit is not set, my requirement is that this is true, this is true, this is true. Now, how can I use the done bit status to perform this implementation? This is true and this I want false if I just use the done bit somewhere. So this is the basic understanding. Once you are coming with this, then we'll go into the instruction, which instruction we can use, and accordingly we will be implementing that. So let me ask someone, Sahil, can you help how this logic, what I was explaining, that once the done bit is set, I don't want this 1y1 to be true. What should I do?
Sir, we have to make some changes in the zeroth rung.
Yeah, correct. That is agreed. So what is that change? Which instruction will help me in implementing the change actually? So this is true, this is true. I want this to be false once the done bit is set. So something to be here, which is controlled by the done bit.
So we can add another examine if open switch.
Correct. So good. So why we want an examine if open? Can you just answer that?
Sir, in normal condition, it will give the output 1, and when we press it, then it will give 0.
So you understand that because it's a negative logic actually. What we want, when these two are true, we want this to be true when the done bit is false. Fine. And whenever you will be, so we can have something here which is controlled by the done bit. And then once you see the done bit is 0 actually. So let's see that if I just write down, I'm not writing any instructions. I'm just helping others who are not able to visualize to see that if this is something which is rated with a done bit. Now what I want when done bit is 0. Let's try to do that. And this is 1, this is 1. what I want here in 1y1, what should be the state of 1y1? Is it 0 or 1?
Sir, 1.
1, correct. So what we want, once this is 1, and then done bit is 0, I want this to be 1. Now, when the done bit is 1, what should be the state here? So this is 1, I want this to be 0. So now you can easily see that whatever we are expecting out of 1y1 is just a knot of D and. So when done bit is set, I want 1y1 to be 0. When done bit is not set, I want the 1y1 to be 1. So this itself will bring out to the understanding that you have to use something which is of opposite. So whenever you are not giving any signal to the done bit, then it should be true. And that is only possible when we will use instruction XIO. So XIO is a normally closed instructions. It means that if I just draw like this, normally closed, it means that when, and this is controlled by the done bit. So if when the done bit is 0, it is not true. By default, this is true. Fine. So now this representation of the done bit is basically by default, when the done bit is not set, this is now giving me the straight logic that this is true, and this is true, and done bit is 0. Fine. And what we have seen that this is true, if done bit is equal to 1, this will be false. So this XIO instruction idea will come from this understanding. That is the most important part. Once we have this understanding clear, then it is already done. So only you have to just write down the proper address for the done bit over here. And that is how the program will be done for you. So you will be using XIO instruction here. And the address for this is C5:0/DN. So I will be using a output from the counter, which is helping me in stopping the operator to eject the 16th part. So after 15, this done bit is set. And this will not allow the energization of 1y1, even if the operator is pressing S1 again and again. So that is the logic, most important part that we need to add over here. Now, how should I enable it again? Because the statement, so this is done actually, this part is again done here. The last part left out is that the counter must be reset by actuating a push button S2, so that if I give this S2 access to the supervisor who will allow the operator to eject say 15 parts once again, then I have to do something with this S2 push button. And what is that instruction I should add here? Who will tell? Who has not? Hariharan, can you tell? How can I reset everything so that the another 15 blocks can be ejected? Hariharan, are you there in the class?
Yes, sir.
Yeah, so what should be that instruction? See, now the last statement we are implementing, the counter must be reset by actuating the push button S2. So how that will happen? What should I draw here in the last line of the instruction here? Last line of the code. Are you paying attention in the class?
Yes, sir, but I couldn't get properly, sir.
No, you have to spend time, otherwise it will be difficult. Huh? So if you are not.
Yes, sir, I will listen to the importance class for MCL784 sir.
Okay. Fine. So who will tell me this instruction now? Anyone who can raise their hand?
Sir, we can add another switch S2 examine if closed and then reset the done bit.
No, you want an examine if closed? Yeah, correct. So this is what we want. So we'll use another XIC instruction. Good. And this will be controlled by the S2. And what shall I do here?
So reset the done bit.
So we will reset the counter actually. So that is
Yes,
what reset instruction will be used. And we will be just writing the address of the counter over here. That is C5:0. That's all. So on a reset instruction, you will be only writing the address of the counter or timer which you want to reset. So once you put this instruction S2, it will be resetting the counter C5, and then your problem will be done. So this is the solution of this problem, which we have done and we have discussed. And anyone has a doubt about this, or is there any other method you have tried it out and that is also working? you can just let us know. This is the one default we understood that how it can be done.
Sir, if we do not use any switch S2, can we use XIC done bit again in the second rung?
No, XIC done bit, it means that without supervisor intervention, you are resetting it. It means that again you are giving freedom to the operator, which we don't want. See, our
I actually wanted to ask, can we use again the done bit again?
Yeah, done bit can be used again. Yeah, you can use any of the instructions. See, physically they are one devices, but by using the different instruction and addresses, you can use that multiple times in the program. There is no limitation on that.
Okay.
So I can use even the S1 again. It doesn't mean that I have utilized S1 once. I can't use S1 anywhere again. That is not the case. You can use these instructions as many times in the program. I can read the state of S1 again and then combine it with another instruction to check something and then take action. So that is permissible. So same way you can use the done bit again, maybe with a different instruction also. It's not that the done bit is now bound to used with XIO only. I can use done bit with the again XIC instruction as well. So I can combine that with some other to just energize something else. So that is open, that you can use these instructions freely within the ladder, and you can place these addresses as required. Right?
Yes, sir. Sir, shall we use counter done bit before S2 in series so that even if supervisor presses the key, it won't work before 15 have been counted?
Yeah, that is also, so you can add additional interlocks. What you are suggesting is a nice thing, and we most of the time take care of. So right now we are just writing a simple program, but in the actual industrial application, whenever we do this kind of implementation, interlocks are very important. Actually, interlocks means when you are binding someone to do this. So only when this condition happens, then only the next operation will take place, and that is what we call interlocking. So we can add additional interlocking into this. So what you are trying to say is right, that even pressing S2 will not reset the counter, because right now there is a danger that if the supervisor reset in between also, the counter will reset.
Yes, sir.
So that is fine. I think that's a good idea that it can be added. So those interlocks are most welcome. They can be added.
Okay, sir.
Yeah, anyone else adding something?
Sir, can we not use latching and unlatching? Suppose in place of 1y1 we use latching, and after the counter reaches 15, using the DN bit we unlatch the 1y1.
So let me just explain that what you are saying. First of all, whenever so latching unlatching depends on what kind of a pneumatic circuit you are using. See, we will use the latching unlatching instructions only when there is a chance that once you remove this input, the wall will go to the default position. So whenever we are using a 2-position wall like this, as I have explained in the beginning itself, that in this wall, once you energize 1y1, the state of the spool will remain here only, even if you remove the current from 1y1. It is almost like a latching. See, once you give a current into 1y1, and if I'm not even using a simple OT instruction, it is almost like latching, because the state of the 1y1 will not change. So latching unlatching instruction will come when you want to keep it on for some time. And I don't see in the current configuration of the direction control wall, you need to keep it on all the time. Just one momentary pulse to just shift the spool to one end will be good enough actually.
Yes, sir.
Is that
Thank
right?
you, sir.
So that is why the latching and unlatching will not be required here. If I would have been added a spring offset valve, that is what I have explained earlier. So you could be ready and you can attempt the same problem with that kind of valve also. Then the latching unlatching will come into picture. So I think that's a problem idea that you have given. You can try out the same problem what we have done here. But instead of using this 1y2, you can try out yourself by using the spring over here. Same wall with a spring on one side, then your ladder logic will change. And then certainly you may be looking forward to use the latching and unlatching instructions. Is that right?
Yes, sir. Understood.
Good, sir.
Thank you.
So I hope that with these two problems, at least you get some insight how to attempt this, and we have more problems to solve. What I will do, I will just give those problem statements as an assignment or homework. You try it yourself, and if you are not able to do yourself, then we'll discuss in the class. Now today what we will do, we'll quickly go through the few left out instructions, though we are almost at the end of the class, but let's have a look at that. So comparison instructions are the one that we should understand, and that is what is the next thing we need to learn here. First of all, let's try to learn the bit file. Actually, that was not taught earlier, but I was looking at that the Onkar, while taking the lab, he is insisting and explaining the use of a bit file actually. Now what we have seen till now, we have seen the input file, we have seen the output file, timer, and the counter files. That all these are the 4 type of files we have seen till now. Now there's a file which is known as binary or the bit file, the binary file. It's again in a memory space inside the PLC. And this is the way you can see in your software also, that you can click it and you can see the complete table of the memory coming in. So if you see that how it has been organized, you can visualize from there. So this is the table you can see. So address is that B3:0, that is a word 1, word 0 basically here. This is the first word here, second word, third word, and so on. So 0, 1, 2, and so on. And each word is 16-bit long, that you can visualize from here. And these are the zeros representing the state of those bits. So these are the memory inside the PLC. But these memory are not mapped with any physical interface outside. Your input and output, they are directly mapped with the input and output connections outside the PLC. So the moment you read the 0, it will be possible only when you will be getting a 0 volt or 24 volt and the input. So physically anything changes outside, it will be immediately reflecting inside the memory on the input file. Same way your program writes something onto this output file, immediately the voltage is available outside the PLC. So physically you will be seeing the voltage being connected with the status of the bit inside these files. It means that input and output files have a direct connection with the external interfaces. Now many times we will be using a bit or the memory location which is not connected anywhere outside. Just for our internal logic development, we will be using that. So this bit file is kind of a file which is having a memory map inside it, but this bit file is not having any impact on the external devices that are connected directly. So it can be used to read and write something. It's a kind of a temporary storage of the state. So what you can do, if you can write, for example, 1 at this location, let me see. So you can just write 1 here, and you can read it actually. So you will be writing as a output of some instructions that you will be executing, and then you will be reading that in another instruction. So that is the kind of a temporary storage for your decision making. So these binary files are utilized for that functionality. Right. So this is the bit file, and that is how the address will be same. So you will be addressing as a B3:0 as the first word. B3:1 is the second word, 3:2 is the third word, and then you put a slash and you will be referring to individual bit over here. And that bit number will appear after the slash. So then you will be able to address the whole memory map of bit file by using this kind of an addressing here. Fine. Then there's an integer file which is important, because when we talk about the comparison instruction, this integer file is also important here. Now integer file, because we are writing in a complete integer, which is a 16-bit integer, you need not to address the bitwise locations. We are not concerned about the bit locations. So there's only one single value will be stored, which is in a 16-bit value here at a particular address locations, and this integer file is addressed by the n. So n7:0 is a complete 16-bit location, and you will be storing one value at that location. So you have similarly multiple words over here, n7:0, 1, 2, 3, 4, 5, and you will be writing those, reading and writing. So these are just an internal memory maps where you will be reading and writing certain values or certain type of values inside. So binary file is writing the bit values. Integer file you will be writing the integer values, and same is with the float. So we will be using till integer, not the float part right now in the program. So this is the way you should be understanding the addressing of the integers, because that is required whenever you store for the comparison part. Now, when it comes to the comparison instruction, like all the programming languages, you need to use the logical comparison here. And these are the standard comparison instruction: equal to, not equal to, less than, equal to, greater than or equal to. And there are two additional instructions which are not available as it is in other programming language, but we will be using in the PLC. That is the MEQ and LIM instructions. Mask if equal. So first you mask certain bits and then check if it is equal. And the second one is the limit, to check within the upper bound and the lower bound. The value lies within that bound, then only it will be true. So these are the two additional instructions, MEQ and LIM, that we will discuss in the next class. But rest of the instructions are also very straightforward, that if you can understand the block over here like this, I will explain equal instruction. I will repeat the same again in the next class, but let's try to just have a quick look at that. So this is the block again, as you are writing other instructions graphically, same way you will also be writing a comparison instructions in a graphical form. You have a EQU instruction. Now what you want to compare, you will be comparing two sources over here. So source A and source B. You will be comparing the two values coming from two different sources. And if that is true, they are equal actually, then the output of this is true. So it will be checking, this equal instruction will be checking whether source A is equal to source B. If they are equal, then this will be true. If they are not equal, then this will be false. That's the way the EQU instruction can be used in this case. Fine. Now, what is coming in what you will be writing in the source A and source B? You will be either writing a address here, or you will be writing in a constant value as well. That is also possible. So what you can see here, I will be writing an address over here, that is B3:2. That is one location 16-bit in the memory register. And then I will be comparing it with another value, which is an integer over here. So all sort of comparison, please understand, they will be happening at the bit level only. So finally, whenever you will be writing an integer value, it is converted to the equivalent binary and then it being compared here. Fine. So in that case, N7:4, the value whatever is written over there, it will compare. And if these two values are equal, then this will be true. The second thing is possible that I will be reading this value, but I will be comparing against the constant over. So I will be comparing it with a constant. So instead of N7:4, I can write 210. So then this source B could be a constant value and source A will be the address value. There is no point in placing both the source A, source B constant, because you already know the output. There is nothing. So if I write 200 here, I will easily understand they are 200, 210, they are not equal. So this will be false. So this kind of instructions doesn't make any sense. So that is what it has been written. Either source A could be the address here, and source B could be the address as well as the constant. So you will be either comparing a variable with a constant, or you will be comparing both as a variable, but comparing both as a constant doesn't make any sense. So that is the standard way that you will be doing the comparison here. And all the instructions are like this only. Not equal means only thing they are checking that these two values are not equal. Then there's a less than instructions. When source A is less than source B, then it will be true. Less than or equal to, when the source A is less than or equal to source B, then it is true. Otherwise it is false. Same is for the greater than and greater than equal to. So these basic comparison instructions are almost same, except that what exactly is the logic that you want to compare here. The rest is the MEQ and LIM that we'll discuss in the next class. So just we'll take the next 2-3 minutes to discuss the quiz option, because Prashasti was just mentioning